There we go. Now we're recording. So for this first one here, we can say, well, we can use the sum and difference rules to split up the derivative over the terms. So, this will be like, oh, hang on, I'm still in blue. This will be like the derivative of 5x squared minus the derivative of 3x plus the derivative of 8, right? So for each of these, we can pull out a pull out a constant multiple if we want to. We will. And we won't bother doing that with this one. This is just the derivative of 8. So the derivative of 8 is 0, isn't it? Because the constant rule says that, as we've discovered, the derivative of any constant function is 0. So that's just 0. And then we just have to worry about the first two terms. So for each of these, we're going to apply the power rule. So we're going to get 5 times, and then we'll bring the 2 down. Whatever power we have there, we'll bring it down and multiply it by x to the power 1 less. So this is 2x to the power 1. And then with the dx, the derivative of just x, this is like x to the power 1, right? That's what x is. X can be thought of as x to the power 1. So I bring the 1 down and multiply it by x to the power 0, which is 1 less. You don't actually have to do this. I think I just taught you that the derivative of x is 1, full stop. You can just memorize that fact. But technically, the power rule does also apply because x to the power 0 is indeed 1. So what we have here as a final answer is 10x minus 3. Okay, and if you looked at this and you said that's just 10x minus 3, and you didn't do all of this intermediate work, that's great. Good. I want you all to be at that point eventually within, a week or so. For simple functions like polynomials, derivatives will become pretty much immediate. Okay. 10x minus 3. Boom. Second one, we have a square root function. Now, I haven't taught you what to do with a composition of functions. This right here is a composition of functions. We have 2 functions here. We have a 5x function on the inside, and we have a square root function on the outside. I haven't taught you how to handle composition of functions when you're doing a derivative. I will teach you that. It's called the chain rule. It's coming up next week. But for now, what we can do instead is we can apply a little algebra before we do anything with derivatives. We can just say, hey, if you're taking the square root of 2 things multiplied together, square roots like distribute over multiplication. So you get the square root of the first thing times the square root of the second thing, like that. Then we can say, hey, the square root of 5 is just a constant. So we can use the constant multiple rule to pull out the square root of 5. And now we just have the square root of x. Now, the square root of x is a function that doesn't look like something we've learned how to differentiate, but it is, because a square root is just a power function in disguise, right? So let's take off that mask and say, hey, power function, reveal yourself. Show me your power. It's 1/2. So we can apply the power rule there, right? So what we get here is the square root of 5 times, and then applying the power rule will bring the power down, right? 1/2 x to the power, and then we got to do 1/2 minus 1. You guys did this yesterday, remember? So this is negative 1/2, like that. And this would be a perfectly fine final answer. But if you wanted to take it a little further, you could have also written square root of 5 divided by 2 times the square root of x. This would have been a perfectly good final answer as well. These 2 final answers are equivalent to each other. Either one of these is fine. They're both the correct derivative. I am not picky about simplifying results. Like you do a derivative, as long as you got the derivative and it's correct, it's fine. Like you don't have to simplify it. Okay, at least not now, not in chapter 3. In chapter 4, we will have good reason to simplify it. So that's when we're going to want to do that because there's a purpose to it. But as long as we're just, if it's the final answer, there's no reason to simplify it. So just don't bother. Okay, so that's my policy on simplifying. Questions on that one? Mainly focused on just like, I want you to mainly focus your attention on the strategy here. The idea of like, splitting that up and then constant multiple rule, power rule. Isn't it nice to do derivatives this way instead of the long way? We could, any one of these, we could have done the derivative the long way and we should get the same answer. It would just take, a whole page, right? So, last one. Okay, you might be looking at this and be thinking, well, hey, it's one thing divided by another thing. Like, that's division. You haven't really taught us how to do that, Tristan. That's true. We're going to learn that today. It's called the quotient rule. But in this case, we don't actually need the quotient rule. We can look at it more so like this. We can look at it, we can simplify this into two separate terms by distributing the division. Remember that division distributes over addition, the same way multiplication distributes over addition, because, division is multiplication, just multiplying by a reciprocal of something. So it follows the same rule for distributing. So we have that. So we can take each of the terms in the numerator, x and 3, divide each of them by x squared, and now we have two fractions added together. Now, the first one simplifies. There's an x factor that cancels out here. So one of these x's can cancel with one of those x's. We reduce this to 1 over x, and then this is 3 over x squared. Okay, so now we have two functions, each of which is simpler. But the question remains, how do we apply the power rule? Because in order to use the power rule, which is like sort of our main tool right now, we need let me just do this first. That's the sum rule, right? And then we could even take this 3. We could take this 3 and pull this 3 out using the constant multiple. I'm getting us as far as we can go without using the power rule. Okay, so now the things we actually need to differentiate are 1 over x and 1 over x squared. How do we do that with the power rule?
Can we write them in form of like x power negative 1 and x power negative 2?
Fantastic. Yes, they are like the square root. They are power functions in disguise, right? So if they reveal to us their powers, right? X to the negative 1 and x to the negative 2. Then we can apply the power rule to differentiate them. Let's do it. Negative 1 times x to the negative, x to the what? Subtract 1. Becomes more negative. Negative 1 minus 1 is negative 2, right? Plus 3 times, and then we'll do power function here. So bring power rule again. We'll bring the negative 2, and then x to the power. Okay, negative 2 minus 1, right? Becomes more negative, so it goes down to negative 3. Like that. Okay, so I guess our final answer here can be This would be a perfectly good final answer. Or if you want, you can write it like this. And that's fine too. Okay. Thank you, Squirtle, our MC for the morning. We move on. What do you think, folks? Questions? Okay. Hearing pretty quiet, so you can go ahead and move on. So what we're doing today, continuing with section 3.3, which are differentiation rules. But today we're going to do product rule and quotient rule. Okay, so the first one we're going to do, the product rule. This is going to tell us how we can do the derivative of two functions multiplied together. So just for generality, we're going to call them f of x and g of x. Okay, so these could be any two functions. Like it could be x times the square root of x, or it could be like x squared plus 5 times x minus 3. Or it could even be like x times sine of x, or, you know, sine of x times e to the x, or whatever. Anytime you have two functions multiplied together, that's the sort of situation we're talking about here. Okay. I know I haven't taught you how to do derivatives of sine and e, but we'll get to those soon enough. Okay. So in order to explore this and obtain a rule to put here, let's do this. Let's say you've got a rectangle, and the width of the rectangle is f of x, and the height of the rectangle is g of x. Okay, then the area of the rectangle is f of x times g of x. Okay. If x increases by a little bit, delta x, how fast is the area increasing? That's basically what we want to know here. Because our what do I want to say? Our hang on. I don't know why my brain kind of just like hit a roadblock or something. Okay, so we want to know like the rate of change in the product, right? We want to know like the derivative of the product, right? Instantaneous rate of change in f of x times g of x. And so we're going to study the area of this rectangle. This rectangle is just sort of a construct to help us approach the problem. Okay, it's like, let's kind of visualize this with geometry, and that'll give us a way to kind of work with it. All right. So anyway, what we're going to do is say there's some change in x, and that's like delta x. Now, what happens when there's a change in X? When there's a change in X, anything that depends on X could also change, right? So like f of X here is also going to change by some amount, okay? And g of X is also going to change by some amount. Remember that when functions are sort of like outputs that depend on an input, right? So changing X by a little bit is going to cause a change in f of X, which I'll call delta f of X, the change in f of X. And then it's also going to cause a change in g of X, which I'll call delta g of X, right? So this change in X is causing the two changes in f of X and g of X, respectively. Right now, for the purposes of this picture, I have drawn those changes as positive changes, like they both got bigger. But it doesn't have to be that way. I just, this again, it's just this picture is just sort of a construct to help us figure this out. So for the purpose of the drawing, they'll be positive. They could be negative. It could be whatever. Okay. So what we want to do now is look at this whole region around the outside here. This is the change in the area, right? Oops, I thought that was going to work, but I don't think it did. Oh, I think I know why it didn't work. Because, here we go. Yeah. That's the change in area, right? This is our that area, that's shaded region there, right? That is the change in area. Now, what we want to work with is what we want to find is the derivative of this area, right? We want to basically find the derivative of this product. Okay, so I'm going to write dA over dx is going to be a limit of the change in area divided by the change in x, like that, right? And where change in x goes to 0. Okay, this is going to be, not only is this going to be the derivative of the area, but it's also going to be the derivative of f of x times g of x, because the area is f times g. Does that make sense? So I probably should have written that here as well. Let me get that in there as well. So the first step might be the derivative with respect to x, and I guess let's do this notation of f of x times g of x equals dA over dx, which is this limit of this difference quotient. Now, from the picture, we can figure out what the dA, what the delta A is. It's this region over here, right? But we can kind of break that up into pieces right here and here, right? So what we have here, just looking at like widths and lengths and stuff, okay, we've got f of x times delta g of x. Okay, so here's f of x times change in g of x. And then down here, we have the opposite. We've got the change in f of x times the regular g of x. Okay. And then up in this rectangle, this little tiny rectangle, we have the change times the change. This is change in g times change in f. Okay. So here's what we can do. Add those three things together, and that's the numerator. Okay, so this becomes the limit of we got f of x, or let's write it this way. Let's do delta f of x times g of x plus f of x times delta g of x plus the delta f times delta g, all over delta x. Now, all over delta x, what I actually want to do is divide this by delta x and divide this by delta x and divide this by delta x. Okay. So, and this is as delta x approaches 0. So you see how dividing the entire thing by delta x, I can distribute that division across the three different parts, right? Okay, so this on its own looks an awful lot like a derivative. It's close to being a derivative. This on its own is close to being something like a derivative, but it's not quite. If we're going to split the limit up over the three parts. Okay, so we're going to say limit of the first plus limit of the second plus limit of the third. Okay, and that's always delta x goes to 0. Delta x goes to 0. What we're going to do next here is kind of a subtle point, but one that I think is very important. And that is that this derivative is about, sorry, not this derivative. This limit is about delta x, right? This limit is about delta x, and the parts of the function that are like dependent on delta x are the denominator, delta x, and then the delta f of x. Remember that delta f, that these changes in the outputs of these two functions are caused by the change in the input, right? It's like you change the input and that causes a change in the output, right? So like the parts of this that depend on delta x are those only. This g of x over here does not depend on delta x. It's totally independent. It depends on x, but not delta x. And the x and the change in x are two separate variables that are not related to each other. I mean, they're sort of like related to each other in terms of the idea. They're both related to x, I guess, but like their values are independent. Okay, they're two independent variables. So what that means is that this part, as far as this limit is concerned, because this limit only cares about delta x, this part, the g of x, might as well be a constant. And so any rules that apply to limits that involve constants can apply with the g of x. What we're going to do is we're going to apply the constant multiple rule for limits, which says that you can pull a constant multiple out of the limit. We're going to do that with g of x, not actually because it's constant, but just because it doesn't depend on the variable that this limit is working with, in which case it's like a constant. It may as well be a constant as far as the limit is concerned. This is a subtle point, but I want you guys to get it because it's really important down the line when you study multivariable calculus. I know that's a couple semesters away, but it's still important. It's really important to keep track of what variables are independent of each other and what that means in the context of derivatives and stuff. So here I'm pulling out the g of x, and I just have this left over, change in f divided by change in x, right? Same thing over here. In the second term here, it's the f of x, which is independent, and that part can get pulled out. And the rest of it all depends on the delta, right? So f of x comes out this time. Then I have change in g divided by change in x, like that. And then we have this last one. Now, this last one is a little bit hard to work with. This last one, I'm going to kind of wave my hands around. Because what we're going to do is we're going to say everything's approaching 0, right? Not everything's approaching 0. What I meant to say is the delta x is approaching 0, right? Delta x approaching 0, delta x approaching 0. What I get here is just the derivative of f. What I get here is just the derivative of g. Okay, so far I have that. All right, this is great. right? This is literally the definition of the derivative. That's just literally the limit of the difference quotient for the f function. And then this is the limit of the difference quotient for the g function. Make sure my g looks like a g there, g, right? But the last one is a little bit weird because it's got a change in f times a change in g. If it was just this, that would be f prime, but it's not just that. If it were just this, it would be g prime, but it's not just that. The fact that you have two changes that are both going to be approaching zero means that the overall result here is that what you get is plus zero. It goes to zero. And like I said, I'm going to kind of wave my hands and just ask you to trust me on that one. But I think it kind of makes sense because if you imagine delta x getting smaller, right? If you think about this limit as delta x goes to zero, this is getting tiny, and this is getting tiny, but they still have this genuine length to them, which kind of gives them some substance. This becomes like, this kind of contributes to g prime and this contributes to f prime. But then you would have this tiny little rectangle here that doesn't really have much substance to it. And that part just disappears, basically. It just kind of goes to zero and it becomes inconsequential. It doesn't really contribute anything meaningful to the overall result. So we can ignore the third term there and just take the first two. And there we go. So that is what we get to put up here. I'm going to reorder it a little bit in a way that I think is familiar, that I like here. I like to write it with the f prime first times g, and then f times g prime. And this, my friends, is this is the rule we have to follow when we are doing a derivative of a product. Okay. I'm going to copy that, paste it over on the next page, and then we'll do a couple of examples. Is the third. Okay. All right, there's our product rule. So, for example, if you want to do the derivative of, let's say, x squared plus 5x times 1 over the square root of x, that's a product. We could do that. First of all, let's write 1 over the square root of x as a power function. That's x to the negative 1/2 power, right? 1/2 because it's a square root, negative because it's in the denominator, right? So now with this product here, we can say, let's define f of x is x squared plus 5x, and g of x is x to the negative 1/2. Okay, then we're going to differentiate each of these individually. F prime, if I differentiate this, take a moment to see if you can do the derivative of this. Nice quick derivative, x squared plus 5x. Okay, that's going to be 2x plus 5 using the basic rules like power rule, basically. And then, constant multiple rule and sum and difference rule, sum rule, I guess. Okay, so we got that one. And then let's do this one. Take a moment to see if you can get the derivative of g over here. Okay, this should be negative a half. Negative a half, there we go. X to the power of negative, what's negative a half minus 1? It's negative a half, and then you go minus 1 further down. Right, 0, negative 1, negative 2. Here's negative a half. Subtract 1. We get to there. That's negative 3 halves, or negative 1.5. So I'm going to do the 3 halves there. Okay. Okay, and then I think actually, just for the sake of simplicity, I'm going to write this as negative 1 over 2, 2 from here, times and then this negative x to the 3 halves would be like the square root of x cubed. Remember how that works with fractional exponents, where the denominator is the index of the radical, so it's a square root as opposed to like a cube root or whatever else. And then the numerator is the power that you raise x to, so x cubed. Okay. So what we want to do now is say, all right, what we're going to get from this derivative here, it should be f prime times g plus f times g prime. Okay, that's the format. That is the, here, I'll zoom out a little bit so you can see it. That was our product rule that we discovered, right? By doing that sort of geometry thing with a rectangle. That's what we got to do. That's how it works. So, so now I just had to take the pieces and put them in the right places. So the first thing I have here is f prime, so that's going to go right there. So I have 2x plus 5, and then I need my g. So I'll take g from here and put it over there. So times x to the negative 1/2, and then plus then I take f, right? So I guess I got to grab that guy. That guy there, that's going here. So I got x squared plus 5x. And then I've got g prime, which is this fellow, going right in there. So times, I'll put parentheses, negative 1 over 2 times the square root of x cubed. So there we go. So that's our answer. If we wanted to simplify it ever so slightly, we could. So I might write this as like 2x plus 5 over the square root of x plus, or I guess actually maybe minus, because of that negative right there, minus x squared plus 5x over 2 times the square root of x cubed. And I think that looks like a pretty good, nice sort of condensed final answer for that. And there we go. That's how you use the product rule. Let's check it. Oops, sorry. How do you check your answer? I'm curious. How do you guys check your answers? What's your strategy? I'm assuming you use the internet somehow. You could maybe ask one of the many calculators out there, like Wolfram Alpha, Desmos. Yeah, I recommend using Desmos. I think a graphical approach is always good. And Desmos will be allowed on tests. Things like Mathway and Symbol Lab can check for you, but those won't be allowed on tests. Okay. Folks, I don't I don't really have a problem with the existence of Mathway and Symbol Lab. Like, they're fine tools. They're fine tools. I even use them occasionally myself for like really complicated integrals and derivatives. But like, but yeah, you don't want to use them when you're learning because you don't want to rely too heavily on computers to do things for you, right? So Desmos is a better tool because Desmos doesn't like literally tell you like what the derivative is as a form, you know, in the format of a function. It doesn't tell you that, but it does show you the graph. So what we can do is we can define a function to be our original function here. So, you know, this original function right here, this is our f of x here. Or I shouldn't call it f, maybe let's call it g or h, because we already used f and g earlier. So let's just call that h. Oh no, sorry, that's my scroll wheel. All right, so I'll write h of x equals that. And then times like, you know, 1 over square root x. There we go. When you're typing in Desmos, by the way, SQRT is a nice shortcut for square root. If you guys are using like this thingy with all the symbols and stuff, that's fine, but I do recommend learning how to like type stuff because it's way, way faster. Oops. So there's that. Now, if I just graph h prime of x, then that'll show me the derivative, the graph of the derivative. So in the red here, we have the original function. In the purple, we have its derivative. And so now what I need to do is graph what I found here, which is 2x plus 5 over the square root of x minus another fraction, x squared plus 5x over 2 times the square root of x cubed. And how can we tell if we got it right? The functions should be the same, right? And you can turn them on and off like this to see that they are indeed the same function. And they are. The black and the purple are the same. So that's how I recommend checking if it's during a quiz or something. And practice doing it this way because that's available. Okay. Okay. I wanted to introduce some new derivatives to you, but I'm wondering if it's the right time. Is it the right time? Well, maybe. Let's get the quotient rule down here. I'm not going to go through a derivation of the quotient rule or a proof of it like with the product rule. It's very similar to the product rule. It looks a little bit different. Let's look at it and compare and contrast. Here's the first difference. Instead of adding right here, like in the product rule, adding these two terms, we're going to be subtracting. It's otherwise the same, f prime times g minus f times g prime. But then we have all divided by the original g function squared. Which I'll write like that. Okay. Squared. G of x squared. Okay. So this is sometimes when you're memorizing these things, you might want to sort of simplify them in your head. So like that's how I think of the quotient rule. Okay. F prime g minus fg prime all over g squared. Like that's one way to think about it. You can also there's also versions of this. You'll hear you'll see like sometimes you'll see differentiation rules written out in terms of U's and V's. Instead of F and G, you'll see like, instead of using function names, you'll see it like using variable names. U and V are often like, if you're going to use some other variables, U and V are common. Kind of like we did with U substitution. Okay, U is another common variable that's used, especially for like an intermediary variable between X and Y, which is basically what this is. The D in this case represents derivative. Okay, the D here means derivative of U and derivative of V. Okay. And then another version of this, which is a nice sort of mnemonic, high and low. Okay. And I know those are just abbreviations for the words high and low. High being the numerator, low being the denominator. Okay. This is let's say this is low D high minus high D low all over low squared. That's so low D high minus high D low is kind of a nice, it's not really a mnemonic, but it is sort of like it's a tool that people use to, it's sort of a mnemonic. It's a tool that people use to remember, like memorize this. You guys are going to need to memorize these differentiation rules for chapter 3, but after chapter 3, I'm going to give you a formula sheet to use on subsequent chapters. Okay, 4 and 5. Just a heads up. All right, we'll do more examples next week. In the meantime, work on homework, practice this stuff on your own. I'll be getting a new exercise set out to you soon, which will be due next week on Friday. Okie doke. Bye, everyone.